Hello, students. We all know that metals are strong, they're shiny, and they're very useful materials, right? But their true nature, their real character, that's only revealed when they react. So today, we're going to explore the chemical properties of metals and see what really happens when we put them to the test.
So, here's our plan for today. First, we'll try to understand what makes metals a reactive family. Then we'll look at their reaction with oxygen, the air around us. After that, we'll see how they react with water, and then with acids. Finally, and this is the most important part, we'll put all our observations together to create something called the reactivity series. It's a really powerful tool, you'll see.
All right, let's begin with our first section. We're going to recall what we already know about metals. We see them everywhere, right? In buildings, in cars. We see their physical strength. But the real action, the truly interesting part, happens at the chemical level. So, let's find out what makes them so, eager to react.
Now, you already know about the physical properties of metals, don't you? We know they're shiny, a property we call luster. They are generally hard. They're malleable, which means, you remember, we can beat them into thin sheets. And they're ductile, so they can be drawn into wires. But you see, these are just their physical properties, their outward appearance. A metal's true character, its personality, really comes out when it starts reacting.
But then the question is, how do we actually see this reactivity? How can we tell that one metal is more active than another? Well, it's actually quite simple. We test them. We put them in different situations with different substances and just observe what happens. And we're going to do this systematically, starting with something that's all around us, the air.
So let's begin with our first reaction. We're going to ask a simple question. What happens when metals are burnt in the air? This is a really fundamental reaction, and it tells us a lot about the nature of these metals.
Okay, there's a general rule here, and it's quite straightforward. When a metal reacts with oxygen, it forms something called a metal oxide. So the word equation is simple to remember. Metal plus oxygen gives metal oxide. A classic example of this, something you may have even seen in your school lab, is burning a magnesium ribbon. And when it burns, wow, it burns with a dazzling white flame. It's really bright. And what's left behind is a white powder. That powder is magnesium oxide. The chemical equation for this reaction is 2Mg plus O2 gives 2MgO.
So, we formed this magnesium oxide, but what is its nature? Is it acidic or is it basic? Well, most metal oxides are basic in nature. Now, you might remember from your chapter on acids and bases, what does a base do to litmus paper? That's right, it turns red litmus paper blue. So if we took that white powder, the magnesium oxide, and dissolved it in water, the solution would be basic.
But in chemistry, there are always exceptions, and they are usually very interesting. Some metal oxides, like aluminum oxide and zinc oxide, are special. They are called amphoteric oxides. Now, this is a very, very important term for your exams. Amphoteric means it has a dual nature. It can act like an acid, and it can act like a base. It just depends on what it's reacting with.
Let's take a look at aluminum oxide as an example. See the first reaction on your screen? Here, aluminum oxide is reacting with an acid, HCl. So in this case, it's behaving like a base. But now, look at the second reaction. It's reacting with a strong base, NaOH. So here, it's behaving like an acid. And notice that in both cases, the final products are salt and water. This is exactly what makes it amphoteric.
Now, this property of aluminum forming an oxide layer is actually used in a very practical process called anodizing. You see, aluminum naturally forms a very thin, protective layer of oxide on its own. What anodizing does is it makes this protective layer much, much thicker and stronger. This helps protect the aluminum from corrosion or rusting. You've probably seen anodized materials, like in window frames or even some cooking pots and pans.
Okay, so we're done with oxygen. Let's move on to our next test, reaction with water. Now, water is a fantastic substance to test with because it really shows the huge differences in how reactive metals are. Some react, explosively, while others just sit there and do nothing at all. And when we do these experiments, we see a very clear hierarchy, a kind of ranking. Right at the top, you have metals like potassium and sodium. They react violently, even with cold water. A little less reactive is calcium. It reacts gently with cold water. Then you have magnesium, which needs hot water to react. After that, metals like aluminum, zinc, and iron. They need even more energy, so they only react with steam. And right at the bottom are metals like lead,
copper, silver, and gold. They show no reaction at all. Let's talk about that reaction with sodium, because it's very dramatic. This is something that must be done with extreme care in a lab. You take a tiny piece of sodium, drop it in water, and it just zips around on the surface, fizzing like crazy. It produces hydrogen gas, but the reaction also produces a lot of heat. We call that an exothermic reaction. And there's so much heat that the hydrogen gas produced actually catches fire. So you can see, it's a very vigorous and dangerous reaction.
Here's an interesting question for you. When you put calcium or magnesium in the water, they start reacting, and after a while, they start to float. Why do you think that happens? Any guesses? Well, the reason is the hydrogen gas that's being produced. The bubbles of gas stick to the surface of the metal. This makes the metal less dense. It makes it buoyant, and so it floats up to the surface. It's quite interesting to watch.
Okay, so that's the reactive metals. What about something like iron? If you put an iron nail in a glass of water, nothing really happens, right? It doesn't fizz, it doesn't catch fire. Iron doesn't react with cold water or even hot water, but it does react with steam. If you pass steam over red-hot iron, then a reaction will happen, and you'll get iron oxide and hydrogen gas, as you can see in the equation. All right, time for our third and final test for today. We're now going to see how metals react with dilute acids. This reaction is another great way to compare how reactive different metals are, and it helps us see that final pattern. So, what's the general rule here? It's that a metal, when it reacts with a dilute acid, will produce a salt and hydrogen gas. You can think of it like the metal is more reactive, so it pushes out or displaces the hydrogen from the acid. For example, if zinc reacts with hydrochloric acid, zinc pushes out the hydrogen, and you're left with zinc chloride, which is a salt, and of course, hydrogen gas. But how can we be sure that the gas coming out is actually hydrogen? Well, there's a very simple and famous test for it. You just bring a burning splinter or a matchstick near the mouth of the test tube. If hydrogen gas is present, it will burn with a characteristic pop sound. It's a very clear confirmation. And once again, we have a very important exception that you must remember for your exams. This has to do with nitric acid, or HNO3. When metals react with nitric acid, you usually do not get hydrogen gas. So why is that? It's because nitric acid is a very strong oxidizing agent. This means as soon as any hydrogen gas is formed, the nitric acid immediately oxidizes it and turns it into water. Speaking of powerful acids, let me tell you about a very special mixture called aqua regia. The name literally means royal water in Latin. And why is it called that? Because it's one of the few things on Earth that can dissolve noble metals like gold and platinum, which normally don't react with anything. It's a freshly prepared mixture of concentrated hydrochloric acid and concentrated nitric acid in a 3-to-1 ratio. All right, so we've seen how metals react with oxygen, with water, and with acids. Now, all these different observations, all these different reactions, they are not random. They all point towards a single predictable pattern, and we can arrange this pattern into something we call the reactivity series. This table here is basically the master key to understanding all these reactions. It's a list of common metals, arranged in order of their reactivity, from most reactive at the top to least reactive at the bottom. So you can see potassium, K, is at the very top. It's the most reactive. And as we go down the list, the reactivity keeps decreasing, all the way down to gold, Au, which is the least reactive. Now, notice hydrogen is also in this list. It's there as a reference point. And here's the crucial idea. Any metal that is above hydrogen in this series can displace hydrogen from dilute acids, but any metal below hydrogen, like copper, silver, or gold, they cannot. So, today we've learned that the reactivity of metals follows a very clear and predictable pattern. This reactivity series is more than just a list. It's a very powerful tool that helps us predict reactions. And that leads us to our next big question. Can we use this series to predict what will happen in other types of reactions? For example, what happens when a more reactive metal meets a salt solution of a less reactive metal? Well, that is exactly what we will explore in our next lesson when we talk about displacement reactions.